Hello, pre-calc students. Here's 6.7, a new look at conic sections. The objective is to define conic sections in terms of eccentricity and to classify the graph of a second-degree equation by examining the coefficients in the equation. Now, let's make one thing clear. Don't panic. This is not in the test, but it can give you insights and opportunities for extra credit. It can kind of give you the big picture and what these conic sections are all about. Some of the things we notice in conic sections is, first of all, they're called that because you can get them by slicing a double cone with a plane. And you can look in your book on page 213 for some nice illustrations. The conic sections can all be obtained from a single definition involving focus and a directrix. And that should be can. We used to think that you can only do that with a parabola, as the points equidistant between focus and directions, but we're going to see that we can do and generate all the conic sections with that basic definition. And all the conic sections have second-degree equations in ax squared plus bxy plus cx cy squared and so forth. And we're going to see how you can graph those like that too. Now, here's the common definition of a conic section. Let f be the focus. It's a fixed point. And you've got a fixed line D, the directrix. Let P be a point in a plane of D and F, and consider all the set of points on which the ratio of PF to PD is the constant E. We call this E the eccentricity of the conic section. And depending on where the eccentricity is, will determine what type of conic section you have. If the eccentricity equals 1, then you're basically saying PF ratio PD is 1, so PF equals PD, and that's what we called our definition of the parabola before. But notice if we make the ratios smaller than 1, we get an ellipse, and greater than 1, we get a hyperbola. Let's see how this works. First of all, with this first example, I want to go ahead and try and graph it out, or do it out algebraically. And we're given let's resume it again. Okay. We're given a focus at 0, 3, and the directrix is y equals 12. Find the equation set of all points for PF to PD equals 1/2. Well, I can think that maybe we've got 12 here, so if I go 3 and 6, if I make this point right here for PD, would equal 3/6. Yeah, because these are 9 away. And so if I go 3 from the focus and 6 from the directrix, I get a point right here, and this will end up being our vertex. The other points are trickier, though, because you're going to keep being closer to the focus than you are the directrix, but it's going to be a 1 to 2 ratio, not an equal ratio like we had before. So let's see what kind of shape we end up with here. Because, you know, when we used to go like this and put a point down here, that would be 6 away and 9 away. That's not... 6 to 9 is not the same ratio. We need a 1 to 2 ratio. We could be 6 away and 12 away. So let's see if we can find that point. 6 away from the focus and 12 away from the directrix. That's this whole length down here. So that's going to be somewhere more like along down here somewhere. So let's see what kind of equation we can come up with here by using algebra. PF, the distance from P, so this is some point P, x comma y, to the point F, which is 0, 3. So PF is equal to 1/2 PD, or twice PF equals PD. And PF is the square root of x minus 0 squared plus y minus 3 squared. PD is the distance from this point way down to here, and we can take a look at the point that's way up here. This will be x comma 12. So they have the same, these points on this one will have the same x coordinate, but different y coordinate. So we really just have to take a difference in the y coordinate, so we say 12 minus y. And so we got twice the square root of x squared plus y minus 3 squared equals 12 minus y. And we can go ahead and square both sides. So let's square both sides. Let's see what we get here. 4 times x squared plus y minus 3 squared equals 144 minus 24y plus y squared. So that's 4 times x squared plus y squared minus 6y plus 9 equals 144 minus 24y plus y squared. And so we get 4x squared plus 4y squared minus 24y plus 36 equals 144 minus 24y plus y squared. You get some things canceling here. The minus 24y's cancel out, which does make it a much easier equation to simplify now, because you get subtract a y squared from both sides. 4x squared plus 3y squared equals 108. And if we divide through by 108, we'll get x squared over 27 plus y squared over 36 equals 1. And using our little approaches there, so that's x squared over 3 root 3 squared plus y squared over 6 squared equals 1. And let's see if that matches up with our graph here. With a center at the origin and going 6 each way in the y, that's 1, 2, 3, 4, 5, 6 here. Sure, we got that vertex right. And then 1, 2, 3, 4, 5, 6. So 7's going to be down here. And then 2 square root of 3 the other way, or square root of 27, which is a little bigger than 5. 1, 2, 3, 4, 5. Yeah, see, a little bigger than 5 that way. 1, 2, 3, 4. A little bigger than 5 that way. And there's our ellipse, generated by having that. And it looks like the eccentricity then is, as we said before, that ratio. And so this has an eccentricity of 1/2, the ratio of PF over 2. When the eccentricity is between 0 and 1, you get an ellipse. Now I want to show something on that I worked out with GeoGebra on this. And that's something I've tried for a long time but never quite get. And that's to get this universal definition into a GeoGebra file. I've done it successfully with parabolas before, but never able to get it like this. So here we go. Here's the directrix. Call that D. And it's determined, you can move it around by a couple points here. And here's the focus. And right now I have the eccentricity set at 1. So we're getting a parabola. And you can see if you move things around in here, you keep getting parabolas. And notice this distance here too, this K, and K over KD then, the distance of KF over KD is that ratio is equal to 1. That's where the eccentricity comes from. And you can see that down here. And these two distances are staying the same, KF and KD. So what happens now when we start changing the eccentricity? Well, we get different types of conic sections. Eccentricity up to 6 there, eccentricity back to 1, and now when it's less than 1 it becomes an ellipse and then a circle. Now you might say, hey, what about right here? What about right there at 0.9? That looks pretty parabola-like. But if we move the screen around, you can see that this is just a very eccentric ellipse. And it does form an ellipse way up there at 41. Okay. So let's get our eccentricity back to 1. Same thing with hyperbola. If you zoom out on the hyperbola, that looks like a parabola as well. But you're going to find that through repetitive zooming out, notice it's not getting that parabola shape going as we keep zooming out. It's getting that asymptotic behavior of the hyperbola. Notice when we zoom back in, or if we change this eccentricity, let's just do it right here. If we change the eccentricity to a 1, oh, we really zoomed out now. There you go. Change the eccentricity back to 1. Notice that's the parabola technique. And it's getting closer and closer to becoming a vertical line. But as we go a little bigger than 1, there, now it's approaching asymptotes. But right at 1. So notice that parabola becomes the boundary between conic sections. Less than 1, and we end up with ellipses. Greater than 1, hyperbolas, but right at 1, the eccentricity gives us the parabola. Okay. Back to the screen. Oh, and here's where the extra critical opportunity is. Can you come up with a way to generate this? I think you can see that I use an eccentricity slider, and I have a fixed point F and the directrix D. How do you get GeoGebra to make these? Okay. Now let's back to the other idea, and that's classifying second-degree equations. Equations of the form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0 will be conic sections. Now, we haven't usually dealt with this x times y term. We dealt with it briefly in things like xy equals 6. But now we're going to see how it can all tie in. And here's our old friend, the discriminant, but it's in capital letters because it refers to these coefficients, not the a, b, c of the quadratic formula. But the capital letters here, oddly enough, give the same kind of discriminant-like formula for distinguishing between ellipses, parabolas, and hyperbolas. Let's see how this works. First of all, here's the proof. We solved the general equation for y as a function of x. And a little tricky. We got to get our y squared terms, our y terms, and our non-y terms. Plug it in the quadratic formula. And I want to look carefully at what this thing is, this discriminant down underneath here. This thing under the radical. Expression on the radical. What kind of parabola is going to be is determined by b squared minus 4ac. And if it's less than 0, you end up with a square root of a sad parabola. If it's equal to 0, you have a square root of a line. And if it's greater than 0, you have a square root of a happy parabola. And we're going to see this in our diagram in a second. First of all, we can use our rule to identify the graph of this equation. And that is, look at b squared minus 4ac. So the b coefficient there is 2, a is 1, and c is 3. So we get negative 2 squared minus 4 times 1 times 3. 4 minus 12 is negative 8. It's negative, so it's b squared minus 4ac is less than 0, so it's going to be an ellipse. So therefore we've got an ellipse. Now let's test this out with the conic section graph I developed. General conics. And what we want to do is change our sliders to match this with basically a equals 1, b equals negative 2, c equals 3, and this is actually the coefficient f. So we got to get the other ones to 0. So let's get those fixed. A equals 1. So slide this to 1. 1, exactly 1, exactly 1. There we go. B to 2. Actually, it was negative 2, wasn't it? Yeah, negative 2. C was equal to a 3, I believe. I have a hard time with the precision on this. C was equal to 3. There we go. D and E were 0, so we can get that fixed. Okay, 0. And F was, I believe, 1. Now it's not showing up. I got to check these coefficients. When it's not showing up like this, it means that it's a degenerate conic. It somehow totally magically managed to miss the cone. So let's look back at my notes here. F is -1. Oh, that's going to make a difference. So let's go back to that. If we set F to -1, now we suddenly get a conic. And there it is. There is our nice little ellipse. Notice the twisting we have on here because of the xy term. Whereas normally if we had both x squareds and y squareds, we would say horizontal and vertical ellipse and so forth, but in this case that xy gives it a little bit of rotation. Okay, I also want to make a connection to what we talked about earlier, that why is this an ellipse? When we solve that general equation for y, we got this huge equation. And notice the thing underneath the radical then determines what kind of shape you're going to have. And it's specifically b squared minus 4ac. In our graph over here, this ellipse comes from taking the square root of this sad parabola, giving you this section. Now you might wonder why, if you're taking the square root of positive numbers, do you get negatives? Well, that's because you still have to add and subtract this number, 2x over 2c. So you're basically adding a line to it, and that's what's giving it that little twist. But it still is, in essence, an ellipse, and notice how its domain is restricted to where this sad parabola is positive. We don't generate points for these things. Now we can also look to see on GeoGebra how this changes as we start moving some of the constants around. Notice D, E, and F are not part of this b squared minus 4ac. And so as we move D, E, and F around, it still stays a parabola, or still stays an ellipse. Move E around, still basically staying in ellipse. We're changing some of the domain and so forth, basically it's staying in ellipse like that. It's when we start messing with the C's, the A's, and the B's that things change. So notice here, let's start moving B around. Well, in this case, it's not really changing. Now, why wouldn't it? Because B is being squared, so whether it's positive or negative, the b squared minus 4ac is staying greater than 0, because A and C are both positive. Oh, no, there you go. See, I just didn't make B big enough. And now we're getting hyperbolas and so forth. Because it switches from a sad to a happy parabola. Let's mess with the A's. Same type of things going on there. And here you can really see it, that we've got a happy parabola now as this thing underneath the radical. And we can't take the square root of the negative parts, we're going to take the square root of the positive parts, and they end up being two separate sections. And messing with C changes things too. Whoa, Neller. Notice when you get a straight line though, we just get the plain old parabola. Our eccentricity b squared minus 4ac. Now that might not be quite a perfect line. Let's investigate. Do we really have... It's not letting me move. That's it. That's why I was doing that. Okay. See if we got another section down here. No. No, because basically the b squared minus 4ac has become a... it is, look at the equation there, 0.04. Maybe we can tweak this a little more to make it perfectly. So this is still technically going to be a hyperbola, and we should see something way over here somewhere. Let's go look for it. Maybe not. Oh, see, I'm seeing it bend. There's the bending line. It's just that, well, it's going to be way over here where the radicand formula gets positive. And now we should start seeing the rest of our conic section in here somewhere. Where did it go? Yeah, if this is all the radical, we should be taking the square root. And the square should be down here. But you know what? The other values are so high, I think it's going to be way off in the distance down here somewhere. Because of the negatives and everything like that. Let's find that by zooming out. Keep zooming out. There we go. So close. So let's keep tweaking this and make sure we get our parabola now by having this red thing, the radicand, become a straight line. And that happens right about, maybe we change B a little bit. Oh, it's still on that plus minus thing. There we go, gotta grab her again. Here we go. See, we can change B a little bit there. And get that line to be perfectly straight. Because you have to get B squared minus 4x equal to 0. Maybe if we made these other values like 1. There we go. And met A equal to 1. Here we go. And met B equal to something like there. Now B squared minus 4ac is exactly 1. And if we go back and zoom in now, we can see clearly you don't have the hyperbola anymore. It's strictly a parabola because we're taking the square root of a line. So we only get to one branch. And zooming in. Keep zooming in. Gotta be careful not to be touching one of the equations as you're zooming in, or it tends to start drifting over. And we can zoom a little more here. So this line goes through about 0.16, so we get a little bit over here. And there's your parabola. Okay, let's finish up with kind of a cool demonstration you can do with the 5-point generator. I hope you can have some fun with this, making all sorts of different shapes very quickly. With GeoGebra. And let's go to the 5-point generator. And let's go ahead and just ignore now, just view the graphics view. And do a conic through 5 points. 1. View graphics. And let's get rid of this part. And I don't know if we don't need the axis. Take the axis away. And let's just look at 5 points. 1, 2, 3, 4, 5. And you can move these around to generate all sorts of things. See, there's your ellipse. Just move this one around a little bit. Now it's hyperbola. Somewhere in between them, there's that magic parabola. Sometimes people think this is a parabola, but no, I think that's going to be an ellipse, right? And you can see, again, the parabola is the boundary between the ellipses and the hyperbola. Sometimes the conics will degenerate, just become 2 lines, if you set up the points that way. And so here's where the fun comes. Let's look at A here. See how A can sweep across there. Let's try something. Click on this whole thing and have it do the add the object properties. And you go here to show trace. I think you know where we're going with this. And now we grab A. And we can see all those shapes it makes. Okay, we'll have fun with that. Some neat graphics. Flange out.